In this episode of Remote Trigonometry, we will be going over the basics of arc length and area of a sector. We have a couple of pie chart examples here. In this pie chart, the blue area is 25% of the circle. That means 25% of the angle rotation. It's 25% of the area. It's also 25% of the length along that blue sector. So 25% is a nice number to work with. It's a quarter of a circle. A quarter or 1/4 of a circle is 90 degrees out of 360 degrees. So that fraction or percent of the circle is also the percent of the area covered by the blue sector, and it's that percent of the length along the entire outside curve or circumference of the circle. So the angle gives you what fraction or percent of the circle, and then you apply that percent to the entire area of the circle. So if my radius was 10 centimeters, then the area would be pi r squared, or 100 pi. 25% or 1/4 of 100 pi is approximately 78.54 square centimeters. So that's the area of the blue part. If I wanted the area of the orange part, it's 75% of the entire area. So 0.75 times pi r squared, 100 pi, is approximately 235.62 square centimeters. The circumference of a circle is 2 times pi times radius. And so if my radius was 10, then 2 times 10 is 20. So the circumference all the way around the circle would be 20 pi. So the length along the blue part is 25% of 20 pi, or approximately 15.71 centimeters. If I wanted the length along the orange part, that's the arc length along the orange part, it's 75% of 20 pi, or 47.12 centimeters. That applies no matter, what size angles you have. If I have a little tiny angle, 18 degrees, that's 5% of the circle. Then the blue area is covering 5% of the entire area. So 0.05 times 100 pi square centimeters is approximately 15.71 square centimeters. The orange area is 95% of the entire area, or approximately 298.45 square centimeters. If I wanted the length along the blue sector, then it's 5% of the circumference. So 0.05 times 20 pi is actually equal to pi, because 0.05 times 20 is 1. So I have 1 times pi is that length. So that was kind of why I used 5%. I knew it would come out to be a kind of famous length. So 3.14 approximately pi is the length along the blue curve. Now, in terms of formulas that might show up in the book, books often assume you're working in radians, and sometimes you are, but if you're actually working with shapes, a lot of times you actually are talking in degrees and not in radians. So the idea here again was the angle, which I'm going to represent by theta, divided by 360 degrees gives you the fraction or percent of either the area, and the area of a circle is pi times radius squared. So this gives me the area of the sector. If I want arc length, then it's that fraction or percent of 2 times pi times r, because that's the circumference of a circle. And that will give me the arc length. If you're working in radians, then instead of degrees, you're working with radians, and 2 pi radians make up a full rotation. And so this formula turns into theta over 2 pi times pi r squared. And notice the pi's cancel out. And so you get theta divided by 2 times radius squared. And you'll see that formula, but that assumes you're working with radians, not degrees. So don't use that if you're plugging in an angle in degrees. This formula, if you're working in, so I guess we'll put this because they're not exactly equal. This formula, if you put in radians, is going to be theta over 2 pi times 2 pi r, and the 2's divide out, the pi's divide out, and you get theta times r. So this is arc length if you are working with radians. So, you know, just be aware of what unit you're working with, okay? If you're working with radians, then they do kind of clean up. If you're working with degrees, then you're going to use 360, and the formula itself doesn't clean up too much. But I think a lot of times when you're working with shapes, you're going to work with degrees and not radians. Applying this idea, let's suppose we have this nice garden clock, and it has a radius of 30 feet. And we're interested in this section that contains the years. That's a 120-degree angle. If I were interested in the area of this sector, because I needed to buy dirt for that sector, I've already planted this sector, I'm now working on this sector, or I needed mulch, or I needed to figure out how many plants to cover that whole space. The angle's 120 degrees, so that gives me the fraction or percent of the circle I'm interested in. If I were interested in area, then it would be that percent times the area of the entire circle, so pi r squared, and that would give me approximately 941.54 square feet. If I wanted to know how many of these little pale yellow coleus plants I needed along that edge, then that's an arc length problem. But the 120 degrees still tells me what fraction or percent of the arc of the length I need. So 1/3 of the circumference of the circle, so 2 pi r, the radius is 30. And notice here 3 will divide into 30, giving me 10. So I get 2 times pi times 10, or 20 pi. So 62.83 feet of little yellow coleus plants would be needed to cover that whole section.